In this lecture, we study the common base configuration. So in the last lecture, I have explained three different types of configuration, that is a common base, common emitter, common collector. In this, we are studying the common base configuration. Now using this configuration, we are analyzing the operation of the transistor in the common base mode. So, and we are calculating the parameters to design the amplifier. Now here, how to draw the CB configuration, we will see now. CB configuration, first take the transistor. Now here I am taking the NPN transistor. So for the NPN transistor, arrow mark is outside. Now this is the transistor symbol, and the name common base means what? Base is a common terminal for both input and output. Now this is the base, and emitter and collector. So we have to take arrow mark at the emitter, and it is arrow mark is outside. Outside means this is a NPN transistor. This is NPN transistor. So already in the biasing, I have explained that always we have to make this CB junction forward bias. So now that's why we have to apply the forward bias here. Forward bias, we need to apply the forward bias. So how to apply the forward bias? Because emitter terminal is N-type material. To make forward bias, we need to connect the negative terminal to the emitter, and the name we have to give it as a VEE, because this supply is connected to the emitter. So here I am denoting with the same terminal name with a double suffix, and resistor is connected to control the current, and to measure the current in this branch need to connect one ammeter, and the IE current is in the order of milli, so that's why I am connecting the milliammeter, and need to measure the junction voltage. So this is the junction voltage. By using this meter, we are measuring the junction voltage. Name I am giving it as a VEB, because this meter is connected between emitter and base. That's why the name is VEB. Now the supply here, negative is connected to the ammeter. So negative, positive polarities if we take, these are the polarities. And similarly at the output side, always base collector junction we have to make a reverse bias to collect the. So emitter should emit, that's why we are giving the forward bias, and the collector should collect, that's why we have to give the reverse bias at the output. So how to make the reverse bias? If you see, this collector is made up of N-type material. So to make reverse means N-type material should be connected to the positive plate of the battery, and this battery I am giving name it as a VCC, because that battery we are connecting to the collector terminal. The collector C indicated by the C we have to take it as a double suffix, and so supply we are connecting through the resistor, and this resistor name I am taking it as a RC, and the input here we are connecting to the RE. So we can give it as a RE, RC, or R1, R2, and here branch current we need to measure, and IC current is in the order of milli. So here milliammeter is connected to measure the current, and to measure the branch junction voltage between collector and base. So one voltmeter is connected, and this voltmeter parameter we are naming it as a VCB. And if you take the polarities, because the positive terminal is connected, so positive, negative, and positive, negative. So and base is grounded. So this is the diagram for the CB configuration. Input side we need to apply the forward, and output side we need to apply the reverse, and to measure the voltage and current at the input, we need to connect one ammeter voltmeter, and to measure the voltage and current at the output, we need to connect one more ammeter and voltmeter at the output. So this is about the circuit diagram for the CB configuration. Now after that, we need to obtain the input and output characteristics. VI characteristics. Now here we are trying to analyze the relation between voltage and current for the input side. So what is the how to determine means by keeping the output voltage, that is nothing but what, VCB constant, and vary the supply, input supply, and make some voltage or current and note down these two parameters. Then if you observe here, this is the N material and this is a P. It is nothing but a PN junction, and we are applying the forward bias. So by applying a small voltage, here current flows and it operates like a PN junction diode. So that's why if you observe the characteristics, now here to draw the characteristics on the x-axis, we need to take the input voltage VEB or input current IE on the y-axis, and by keeping what fixed? Output voltage fixed. Now here first we fixed the 0 voltage, and for that by observing this input voltage and input current, if you draw the graph, it look like a normal PN junction characteristics, because this is a PN junction and applied forward bias. That's why it is giving the normal PN junction forward characteristics. Now after that, minimize the input supply and put one more value at the output. VCB, take one more value, and again repeat the same procedure. Vary the input supply and note down the input current and input voltage. Thereby, so we get the characteristics like this. Now with this, what you observed, if VCB value is increased, now by increasing the output voltage, if we increase the VCB, then the graph is moving towards to the y-axis. So this is because of the early effect. Means at the early voltages only we are getting the IE current. So how that is, what is early effect or base width modulation? One more name for the early effect is base width modulation. What is that? Now first we will analyze that, and after that we go to the output characteristics. Now this is the early effect. Now this is the NPN transistor. This is NPN transistor. As the output voltage is increased, now here if the output voltage is increased, then with this depletion width of the junction 2, because this is a reverse bias. So junction 2 is reverse biased, so depletion width is increasing, thereby the effective width of the base is reduced. So this is called the early effect or base width modulation. This is also called base width modulation. The width of the base is changing with respect to output voltage. That's why we call it as a base width modulation. So with this, what happens? It leads to, see, if the effective width of the base is reducing, means what? Here the number of charge carriers are less, thereby whatever the electrons come entering into the base, here the recombination will reduce, thereby I see number of charge carriers here, it is recombination is taking less. So more number of charge carriers are entering into the collector. So here the IC current is increasing because of the by increasing the output voltage. This is the first point, and the second point, it leads to one more point is, when the base depletion width is increasing, the effective width of the base is reducing. So then the concentration gradient, charge carrier gradient takes place. So if the area of this base is very less, now from here the majority charge carriers are electrons, but those electrons are here the majority charge carriers are holes, but here it is minority charge carriers. Now here minority charge carriers are electrons, so those minority charge carriers will try to move into the emitter. This is the charge gradient, we say it as a charge gradient or concentration gradient. So because the width is reducing, charge carriers are moving into the emitter, thereby number of charge carriers at the emitter increases, so IE current is increasing. That's why if you see the graph here, it is moving towards to the y-axis, means what? The IE current we are getting at the earliest. That's why the name is early effect. IE current is increasing by increasing the reverse output voltage. And the third one is, further if we increase the reverse bias output voltage, then at one point the complete base width is equal to 0, thereby breakdown takes place in the transistor. Means what? Total emitter current will flow through the collector without any recombination in the base. Now base is disappeared now, so complete emitter charge carriers will move into the collector. So that is called the punch through. So these three are the effects of because of the early effect. By increasing the output voltage, so IC current is increasing, IE current is increasing, and base width, if the base width is reduced or it's become 0, then breakdown is taking place in the transistor. Next, output characteristic. How to obtain the output characteristics means keep the input voltage constant, keep the input current constant, and vary the output supply and observe the output current and output voltage. And for this, if you plot all these values, then the graph look like this. Now if you see here, if I am taking a 5 milliamp at the input, this IE is equal to 5 milli means what? I fixed the 5 milli over here. Then at the output, for all the VC values from 0 to, for all the values, we get the same current. Why? Because in the operation we have studied that IE is equal to IB plus IC, where IB is very, very less, so IE is almost is equal to IC. So that's why whatever the input current we fix, the same current will available at the output. That's why we get the straight lines at the output characteristics. Now here, output characteristics, we are observing the graph we are drawing for the between VCB and IC. So on the x-axis we are taking the VCB, and on the y-axis we are taking the IC, and by keeping the input current IE constant. So this is the characteristics for the CB output characteristics. Now these are the transistor parameters. These are different dimensions are there. That's why we can also call it as a H parameters. So this represented by the H. The value is represented by the H because H parameters we are representing with the H, and we are taking two suffixes. First suffix indicates the parameter, which parameter we are calculating, and second suffix indicates the which configuration. Now this is the common base configuration. That's why second suffix is B, and the first suffix I indicates the input impedance. And R indicates the reverse voltage gain. Similarly, O indicates the output admittance, and F indicates the forward current gain. So now what are these? We will see the definitions. Now here input impedance is the ratio of change in input voltage to the input current. Now from these input characteristics we can calculate these two. Now from this, what is the input voltage? VB is the input voltage. VB is the input voltage, and IE is the input current. If we take the ratio of input voltage to the rate of change in input voltage to change in input current, by keeping the output voltage VCB constant, then we get the input impedance. Similarly, reverse voltage gain. Normally voltage gain means what? Output voltage divided by the input voltage. Here it is reverse, means what? Input voltage divided by the output voltage. Now from this graph, this is the input voltage and this is the output voltage. So if we take the ratio of change in input voltage to the change in output voltage by keeping the IE. Now here in this graph, three parameters are there. We are taking ratio of two parameters and we are keeping another parameter constant. So IE is constant. Similarly, two more parameters are there. Another one is output impedance. So output admittance. Now what is impedance? Impedance is a ratio of voltage to current, but admittance is what? Reciprocal to the impedance. So that is called the here reciprocal means what? Current divided by the voltage. Output admittance means it is the ratio of change in output current to the output voltage. Now this is the output current and this is the output voltage, and by keeping what constant? IE constant. Similarly, forward current gain. What is current gain? Output current divided by the input current is called the current gain. Now here the HFB is ratio of change in output current. Where is that? Change in output current to the change in input current. This. If we take the two ratio of these two parameters by keeping the VCB constant, and we can get the forward current gain. By seeing these parameters, we can design the amplifier. So this is about the CB configuration. Thank you.